It's in a circular orbit about 22,000 miles above the Earth, in line with the equator, and it's going around the Earth in the same direction that the Earth is rotating, and at the same rate that the Earth rotates. So it appears to somebody standing on the Earth, see the person standing on the Earth here, that, okay, technological difficulties, that the satellite is always sitting in the same spot in the sky. GOES is operational. I hope this, I have some slides that have only red on them, so it's red here. I'm a little worried. It's operational as opposed, most of the work we do here at LASP is with NASA research satellites. We have a scientific question we're trying to answer, and we come up with an instrument, and we get funding to fly that instrument that measures something that helps us answer a science question. But the GOES program is part of NOAA. And NOAA is part of the Department of Commerce. And NOAA has a program to monitor weather. And they monitor they do real-time monitoring, which means they need the data right now. It's not something that the data comes down and scientists sit in their offices for the next 6 years and look at the data. 6 years would be optimistic for some of our projects. NOAA does forecasting. You're all familiar with forecasting of weather. Every night you see it on TV. Most of those forecasts actually are NOAA forecasts that the TV people read out loud. They also do nowcasting. Nowcasting is where you can't measure everything all the time, so you measure a few specific things, and then you use your science knowledge and models to say what's going on with all these other things in between what you measured. So what's going on right now based on these few measurements we measure right now rather than everything. Now the reason this is under the Department of Commerce is that things like weather and space weather, and we'll talk about this some more, they impact our country significantly in terms of commerce, shipping things, communication, safety, and the economy, basically. E stands for environment. Oh, that works. Now, we all know what the environment is. It's basically the natural forces that impact everything we do, both in our daily lives and in our technology. Satellite, or Adelaide, basically you're observing from space, which gives you a unique vantage point to look down and see things in great detail, but as part of a bigger picture. When you measure something on the ground or with an airplane, you're just looking at a small spot on the Earth. But with a satellite, you can look down on the whole Earth and you can watch things like weather patterns move down. But you can also look out into space at the drivers of what I'm going to talk to you about, space weather. And you're in space already, and you can measure those things without having to worry about clouds going over or the Earth's atmosphere absorbing ultraviolet or soft X-rays or things like that. So GOES has been part of NOAA for 41 years. October 1975, way back in the last millennium, they launched the first GOES. And that was actually preceded by a few other satellites that were kind of like precursors to the GOES program. Now, GOES has been done in fits and spurts of new technology every so many years. GOES 1 through 3 were spinning satellites and only had a few instruments on them. And they were still out at geostationary orbit and looking down at the Earth. But on a spinning satellite, that's a much harder thing. You can only take a picture of the Earth when it comes around again. GOES 4 through 7 in the 80s had more advanced instrumentation on them. 8 through 12, they switched over to 3 3-axis stabilized pointing platform. So all the instruments that were Earth-looking were always Earth-looking. And they added imaging and sounding of the atmosphere. Sounding is when you're looking at a profile of something through the atmosphere, temperature, water vapor, whatever. And because it was spin stabilized, or 3-axis stabilized and staring at the Earth, they could make lots of measurements all at the same time, as opposed to a spinning spacecraft, which could take a picture with one instrument here, take another picture with another instrument there, or a different type of measurement. Then in the 2000s, they launched the current series of GOES instruments, which are now called 13, 14, and 15. And when they were on the ground, those were called NO and P. So the GOES program has a very weird nomenclature. They have, when it's on the ground and they're building it, they have a letter. And the next series is GOES R. If you're astute, R is not the 16th letter of the alphabet. So when a satellite, a GOES satellite gets launched and put into operation, it gets a number. The next satellite to be launched is usually called GOES Next. So GOES R is GOES Next. There was one GOES that didn't quite make it to orbit, and GOES Q, so this was NO and P, GOES Q was never built. They just stopped with P.
How many are operational still?
That's coming up in another. So the plan for GOES is that the measurements it makes are so vital to our nation that they fly 3. They want 3 up in space all the time. They fly one of them over the east coast of the United States. See, it's over the equator, so it's not quite over the United States. But it takes data over this whole area when it's with the instruments that are looking down. And another one over the west coast, goes east and goes west, another nomenclature. Operating and looking at the Pacific. The east is looking at the Atlantic and most of the United States. West is looking at the Pacific and most of the United States. And then they have a spare that's just sitting there waiting in case one of these breaks. These are so vital to our nation that we have to have a hot spare that we can pull up and put into operation as soon as one of these goes bad. Even if it's just one of the important instruments on one of these goes bad, they have a call-up list that if this instrument dies, then they'll bring up the other one. Here's the answer to the question. They currently have 3 in space now. GOES 13 and 15 are the operational ones, and 14 is sitting on orbit in spares. All 3 of them have some issues or another, but they're making the required measurements. The GOES R series actually has 4, and we've built 4 instruments. All of the instruments are built. The spacecraft are not all built. GOES R, of course, is launching next month, November 4th, hopefully. Knock on simulated wood. And people are so excited about what GOES R has on it and what measurements it'll make that it's going to go into operations right as soon as it finishes commissioning. Any satellite that goes up, we have to take 6 months or so to test out everything, make sure all the data looks good, that all our instruments are working right, and then by sometime mid next year, hopefully, we'll be put into operations, and GOES R will become GOES 16. GOES S is being built right now. The spacecraft is mostly built. The instruments are being put on it as we speak. And GOES T will start being built as soon as GOES R launches, because that team at Lockheed is going to come back and start building GOES T. And I presume when GOES S launches, that team will come back and start building GOES U. So GOES R was built by Lockheed Martin, the spacecraft was. It's a big big bird. It's about 20 feet by 18 feet by 12 feet. I've been in the clean room with it. You can see here's a picture of a man standing next to the satellite and the solar array sticking out. It weighs about 3 tons. Once they fuel it up, it'll weigh about, what is that, 6 tons? Almost 6 tons, 5.5. It's going to be launched, GOES-R itself will be launched November 4th at 5:40 Eastern Time. A nice sunset time, I think, in November. I think we looked it up. It's just before sunset. From Cape Canaveral at Space Launch Complex 41. It will go on Atlas V. These numbers behind it mean that it's going to have 4 solid rocket boosters on it, which means it will take off really, really fast. It takes a village or an entire nation to build one of these things. The way it works is that NOAA doesn't build satellites. They don't know how to build satellites. The part of the government that knows how to build satellites is NASA. So NOAA hires NASA, says, here's a big pile of money. Congress approves all that money, and NASA goes off and contracts all these different companies to do various aspects of the project. There's the space segment led by Lockheed Martin that builds the spacecraft and has all of these subcontractors. There's the ground system segment. I didn't talk about it all really, but all of these satellites need a ground station. That ground station has to be staring at the satellite. It has to receive all the data from it and send commands up immediately. It has to take all that data and process and make data products and disseminate those data products in real time, or as close to real time as you can. That's led by Harris. And there's also the instrument teams. All these different instrument teams built the instruments that I'm going to talk about, including LASP, this building. So we're spread out all over the country, spreading out your taxpayer dollars and mine. So what's on GOES-R? There's the Advanced Baseline Imager. These are the weather instruments. It's probably the biggest instrument on the spacecraft, and it's the one that gets the most attention. We'll talk about what each of these does later, not too much later. Another instrument is the Geostationary Lightning Mapper, which looks like this, another telescope looking down at the Earth, and it's going to measure lightning. All of the weather measurements, all the satellite imagery you'll see on your evening news or on Weather Underground and things like that come from these 2 instruments. There are also space weather instruments, the Solar Ultraviolet Imager, and that's a telescope that looks at the sun and takes images of the sun. There's the Extreme Ultraviolet and X-ray Irradiance Sensors, EXIS, which we built here in LASP in Boulder. There's the Space Environment in Situ Suite, which is a whole bunch of instruments making measurements of particles right around the spacecraft. And then finally there's a magnetometer, which is that long boom sticking out of the spacecraft. You want it on a long boom to get it away from the spacecraft, so if you're measuring magnetic fields, you're not measuring the magnetic fields of the spacecraft, you're measuring the magnetic fields of the environment around it. But wait, that's not all. So there are these things called UPS or UPS, the Unique Payload Services that are also part of GOES. The Data Collection System, or DCS, is basically an antenna that's looking down at the Earth, and it collects data from ground sensors. So NOAA has a network of ground sensors that are measuring things like water table levels, they're measuring tides, there are buoys out in the ocean measuring temperature and currents, there are ground sensors measuring temperature at the surface and above the surface. And all of those have small little radios, transmitters, and GOES-R has this data collection system where it listens to all those, takes all the data, collects it all, packages it together, and then sends it all back down to NOAA for analysis. There's the GRB, goes rebroadcast, which takes data from the satellite that is sent to the ground, processed on the ground, into higher level data products, sent back up to the satellite, and rebroadcast down to the ground again. And anybody with not so cheaper ground station can listen to that rebroadcast and get real-time data from GOES that's been processed, as opposed to the raw data that's coming down on the regular telemetry. Then there is the High Rate Information Transmission and Emergency Managers Weather Information Network. So this is another rebroadcast of data, but it's not just data, it's forecasts, warnings, and alerts. And this is a system designed for managers of emergency response systems and civil defense and such. If there's an emergency going on, they look to this channel on the GOES satellite to find out what's going on. And then finally, there's the SARSAT, the Search and Rescue Satellite Aided Tracking, which is another antenna that's listening and looking down at the Earth, and it's listening to emergency beacons from airplanes, from ships and boats, from people's personal little avalanche warning beacons and things like that. And if one of these beacons goes off, this instrument on GOES senses that, locates where it is, and sends the information down to Earth, and emergency response people can go find that crashed airplane or that person buried under the snow or whatever. So you don't hear about those very often. The ones you hear about all the time are the weather instruments. About a month ago, they had a media event, and all anybody talked about was ABI. A little bit about GLM. They didn't mention any of this other stuff going on GOES, which made those of us who built other things on GOES really sad. My whole family said, "How come Al Roker didn't talk about your instrument?" I said, "I don't know." But Al Roker has good reason to be pretty excited about ABI and GLM. If we look at ABI and compare it to what the current GOES is doing, the current GOES is measuring in about 5 different wavelengths, looking down, taking an image of half of the Earth in all these different wavelengths. And with these different wavelengths, you can sense different things like water vapor and clouds and other things, temperature. GOES-R has 16 different wavelengths and much, much higher resolution. So it has 3 times the number of channels. It has 4 times better spatial resolution. Well, that doesn't look much better, does it? Wish the projector had 4 times better resolution. Anyway, what this would normally show is how much better you could see all the details of this weather system. It's also 5 times faster, where the current GOES takes, can only do maybe 1/5 of the Earth in 5 minutes. The new ABI will scan the entire Earth in all 16 channels, actually in 4 minutes rather than 5 minutes. So it's significantly better. And all the meteorologists are just waiting for that data. GLM, the Geostationary Lightning Mapper, is a new instrument that will be looking down at the Earth and can measure cloud to ground, cloud to cloud, and within a single cloud, lightning. And it will measure and detect how strong that lightning is, when it's occurring, where it's occurring. And that gives forecasters a much better idea of the energy involved in a storm, how significant that storm is, how much of a threat that storm is to people on the ground and airplanes. But there's another kind of weather, and that's space weather. So the sun and the earth are a complex system where the sun is emitting light, it's emitting magnetic fields, it's emitting charged particles, solar wind, things like flares happen and coronal mass ejections, big blobs of plasma, charged particles and magnetic fields come out, and they all interact with the earth. And there's the earth sitting there with its magnetic field, its atmosphere, and all of our technology, satellites flying around it, all of our technology on the ground. We have these long wires wrapped around the earth in our power grid. We have all this sensitive equipment on satellites communicating down through the atmosphere to the earth. We have astronauts in orbit around the earth. And all of that is subject to what we call space weather. I'm glad I didn't put that in red. And here's a drawing, a very, very, very oversimplified version of our understanding of space weather and all the drivers interacting with the Earth and all the various things that can happen at the Earth. Here is a movie example. You probably have seen this one before, and you'll probably see it at every talk this semester. Here we are looking at the sun, and a flare goes off on the sun. And that flare emits a huge blob of charged particles and magnetic fields called a coronal mass ejection. And that takes about 3-4 days to get to the Earth, and it interacts with the Earth's magnetic field. The Earth has this shield around it, but that shield isn't perfect, and it can get rattled up, and the energy from that CME can fall into the Earth at along the poles. All right, I'll give you an example of a perfect storm in terms of space weather. And that happened, and some of you may have heard about it. The last time I talked about space weather stuff, it's actually 7 years ago, I realized. I talked a lot about this event. Happened in 1859, and a British astronomer, Richard Carrington, was observing the sun with his telescope at an observatory, and he saw a flare, a white light flare. So basically a brightening. Today we look at flares mostly in the ultraviolet and X-rays. It's very rare that you actually can see one in visible light. It has to be a really big one. And he watched that flare and drew pictures of it and thought, that's interesting. And then the next day, really weird stuff happened. And Carrington connected that weird stuff to what happened on the sun and thought that, hey, he didn't use the term space weather, but it's all connected. And on Earth in 1859, telegraph operators were the people who saw real effects to it. They had so much power running through their telegraph lines, without turning on their transmitters, they could transmit messages, because there were ground-induced currents, basically. The upper atmosphere had been energized so much, and there were currents moving around that it was inducing currents in these long wires, and they could do their job without even turning things on. In fact, the currents were so large that they had problems with surges and their equipment bursting into flames, and whole telegraph stations burned down. And the aurora, which is a direct result of space weather, with the CME hitting Earth, rattling up the magnetosphere, and charged particles falling in along the Earth's magnetic fields and hitting the Earth's atmosphere and making a pretty light show. They're usually confined to northern latitudes. I grew up in northern Wisconsin, and I saw them once in a while. I, as part of my research, went to Alaska and saw them a lot. I've only seen them once here in Colorado, and because that's pretty far south. But when you have a truly huge storm, the auroral oval, which is usually confined to like 60 degrees north, came all the way down to the Bahamas and tropical regions. All of this is what happened to a big storm in 1859. The only real technology around that was impacted by it was telegraph operators. Now think about today and all the technology we have and all the wires that are spread around the earth and all the satellites we have flying in the around the earth. And we can start to list what is impacted by space weather. If we have a space weather event, you have disruptions and blackouts in communications, emergency response delays, or our systems are delayed or hindered because they can't talk to each other. Satellite operators have problems. They don't know where their satellites are, and the navigation from satellites becomes a problem. You can get cell phone disruptions. Yes, our cell phones talk to towers nearby, but those towers talk to satellites. We transmit data around the world via satellite. HF radio communication. Airplanes use HF to talk to the ground, and it's a requirement that airplanes always be in contact with the ground. And if they can't get in contact with the ground, they have to reroute or land. This is a big impact for flights that fly over the poles. About 2 decades ago, we would have maybe 1 or 2 flights a day flying over the poles. Now we have dozens flying over the poles every day. And if they have to reroute, then they have to go down. They're not using the Great Circle anymore. Here, I'll use a prop. To get from here to here, say Moscow to Washington, D.C., the shortest route is over the pole. It saves a lot of fuel to do that. If you have to go around this way, you're adding half again or more distance to it. And the planes can't carry that much fuel. They have to land and refuel and take off again. And that's a huge impact to commerce. The military is very, very dependent on technology. There's the whole concept of situational awareness. The military needs to know what's going on wherever they have things happening. And they rely on satellites for that. They rely on GPS location. They rely on instant communication via satellites. They rely on satellites looking down at the Earth and watching things happening. And if that's disrupted, that's a big problem. GPS. We've become so dependent on GPS. It's in our cell phones now. It's in our cars. It's everywhere. Ships pulling into ports use GPS rather than they used to have somebody from the port would come in and pilot the ship in. Now they use GPS to do it. Farmers plow these giant fields in the heartland using GPS because they can't drive a straight line for miles and miles and miles. But GPS can be disrupted by space weather. What space weather does is it changes the charge or the ionization of the upper atmosphere, and that changes the refractive index of the atmosphere to radio waves. GPS works. You look up at a satellite, say there's a GPS satellite, there's a GPS satellite, there's a GPS satellite. Triangulation, I'm right here. You can tell me where I am to within a few centimeters or better. Change the index of refraction of the atmosphere. I see a satellite that's really right there over here, and I see this one that's there, and I see that one there, and I triangulate to the wrong position.
Looking through a bubble.
Yeah. A colleague over at NOAA, just across town, he did an experiment. He put his handheld GPS device in his backyard and then waited and recorded the position of his backyard. And a flare went off and it changed the ionization of the upper atmosphere. His GPS said that his backyard moved by 40 meters because of that flare. Now imagine if you're landing an airplane in the fog and or driving a car or whatever. What happens if you're wrong by 40 meters? Not good. all of these charged particles can have direct effect on things like the electronics of satellites. There have been several cases where satellites have been damaged by energetic particles hitting them and ruining basically the electronics, giving them a lobotomy. Power grids. This is a direct comparison to the telegraph operators problem in the Carrington event. They had currents surging through their telegraph lines. Right now we have power grids that are connected all over the planet, and we move energy from one power station to another power station to another community, and if there are extra currents on those lines, it can burn out transformers. And those transformers are not little transformers like you might have in your radio or your cell phone. Those are transformers that are as big as this room and cost millions of dollars and take years to build. If you burn one of those out, it can take years to replace it. And there was a power outage in Canada in the 1980s that was due to a storm, a solar storm. There's also astronaut health and safety. Imagine we're talking about, NASA is talking about sending people to Mars in the next few decades. They're out in their spacecraft going to Mars. It'll take them a year to get there, and they'll be there for a few years, and they won't have the protection of the Earth's magnetic field. They'll be exposed. Now, we could build spacecraft that could hold them, that could shield them, but that would be really, really heavy, really, really thick spacecraft. It's easier to have just a bunker in that spacecraft and know when space weather is going to come with nowcasting and forecasting, and have them hide in that little bunker rather than exposing them to radiation all the time. In fact, people say that the Apollo astronauts going to the moon were very lucky that we didn't have a space weather event that could have zapped them.
There was one of the Apollo flights that after it came back to the Earth, a week later, there was a huge solar flare. And if those astronauts had not come back, they would have gotten fried on the moon.
Yeah.
It was either 12 or 17.
Yeah.
It was one of those two. 1 week later, those guys would have been fried.
They were very lucky.
The impact along the lines of power grid failures is our pipelines.
Right. Right. All of our pipelines are big metal conductors that can carry currents, and those can have problems during space weather events. Now, there's another bullet down here in red, and it tells you about National Academy of Sciences did a study in 2009 to try to assess what our vulnerability is to space weather. Just the United States, but since it was a United States funded study. And they concluded that if a Carrington event, which is a 1 in every 100, 200 years type event, if that occurred today with our technology, the impacts in all these areas would be so severe that it would cost about $1 to $2 trillion to recover from and take several years. It would be like a hurricane had hit the US and wiped out a lot of things. But it would be a space weather hurricane, so to speak. This is just a little table out of a report on our space weather observing systems, current capabilities and requirements for the next decade. That was done in 2013 at the order of the president. The president now gets daily space weather updates as part of his morning briefings because it has such an impact onto everything we're doing, particularly military and commerce. But this is just kind of a flow down of the different types of energy drivers coming from the sun, where they're having an impact, what systems are affected, what the impacts are, how we should respond to all those impacts. And they've come up with, this is just the top level of a huge decision tree of what to do. And from that, they've come up with lots and lots of requirements. Those of us who build things know all about requirements. NOAA is tasked with monitoring space weather, and the Space Weather Prediction Center, which is just across town on Broadway, part of the Department of Commerce campus. It's part of the National Weather Service and the National Centers for Environmental Prediction. And they have to watch, I counted, about 70 different parameters that are all related to space weather. And about a quarter of these are being met by GOES-R. The others are by ground measurements and satellites in different orbits. So running out of time, let's talk about the space weather instruments. We've had a lot of advances in understanding space weather because of NASA research satellites, because of data analysis and theory done by people all over the world, and understand quite a bit more about space weather than we did in the past. And that's where we come up with that long list of things to measure. The GOES-R is the result of that knowledge from about 10 years ago. Because I've been working on GOES-R since 2004. All of our designs were put in cement or steel in aluminum 2006. So 10 years ago, we built these instruments as the state of the art and state of the science. And that's my disclaimer if they don't work right. But we're still really excited because they're a lot better than the 20-year-old state-of-the-art measurements that are currently being made. So GOES-R has all of those space weather sensors and the weather sensors and all the other things sticking out from the spacecraft, and it will give us better detection of things happening on the sun, coronal holes, solar flares, CMEs, the different source regions of all the activity on the sun. It'll give us better, more accurate monitoring of energetic particles coming from the sun, and in the vicinity of the spacecraft. It will improve forecasts for power outages and better warnings for any of the other things that we saw on the that previous slide listing all those various space weather impacts. One of the instruments, which is actually 5 instruments, or 6, I can count. Oh, that's not an instrument, it's just the brain. SICE is the Space Environment In Situ Suite. So SICE is a bunch of instruments, 5 instruments and a brain, that are sitting on the side of the spacecraft, and they're measuring in situ, in place, the particles that are hitting the spacecraft. And they're measuring protons and electrons and heavier ions with these instruments. And these instruments are giving a much higher energy resolution, a larger dynamic range of energies, and so they'll be used for assessing the various risks to satellites and astronauts, and also of any events that might cause disruptions in the ionosphere and everything that cascades down from that. And the SICE instruments were built by ATC, which stands for Assurance Technology Corporation, I believe. Was there a question? I thought I saw a hand. The magnetometer is sitting out here on the end of this long boom. I forget how long the boom is on this GOES. On some it's been as long as 10 meters. Might be even longer than that. But like I said before, it's stuck out way away from the spacecraft so that any magnetic fields that the spacecraft itself generates don't affect it as much. And it's measuring the magnetic fields where the spacecraft are. Now GOES is out far enough that sometimes it's inside the magnetosphere and sometimes it's outside the magnetosphere. And so it's kind of mapping what's going on in geostationary orbit and measuring the strength of those magnetic fields and also the strength of how the magnetic fields are disrupted by solar storms coming and hitting them. Another instrument is called SUVI. Actually, I didn't say who built. The magnetometer is built by Orbital ATK, and I cannot remember what ATK stands for. They weren't Orbital when they started, they were ATK, and then they got bought out. SUVI was built by Lockheed in Palo Alto, the Lockheed Martin Space Astronomy Lab, is that what it stands for? Bill used to work there, so he knows. SUVI is right here on the yoke of the solar array. So the main body of the GOES spacecraft is fixed to always be pointing down at the Earth and taking all those great weather images. All these instruments that want to look at the sun have to be on a platform pointed at the sun. And they do that by putting them on the big bracket that holds the solar array, because the solar array has to track the sun in order to power the spacecraft. So as the spacecraft is pointing down at Earth and going around Earth, the solar array is like a big sail that's rotating around and always looking at the sun. And then in that yoke, we have a platform that can point up or down and keep the sun lined up in perfect targeting for all of those instruments that need to look directly at the sun. So SUVI is an ultraviolet telescope that can measure in 6 different wavelengths in the extreme ultraviolet and ultraviolet. And here's some examples. They're much prettier in color and non-green color. But SUVI is, you've probably all seen images from SDO, the Solar Dynamics Observatory. Same people that built the solar imager on SDO built the one for GOES and used the same ideas and similar wavelengths to look for features on the sun that might be coronal holes, which have magnetic fields and particles streaming out and hitting the Earth. They can locate flares when they occur, and CMEs, and they can look at active regions, which in the visible look dark, but in the ultraviolet and X-rays are very, very bright and can change rapidly and affect how much ionizing energy is reaching the Earth. And they can look at those and tell you how they're evolving and how the magnetic fields are changing and give you an indication of whether there's going to be a flare or not, depending on how complex a region is. Flares usually occur when a solar active region, which is a knot of magnetic fields, gets really complex and it wants to release energy and become simpler, and that's when a flare occurs. And a flare is a brightening of short wavelengths like X-rays and ultraviolet of the sun, and one spot like this on the sun can suddenly in X-rays be 10 times or 100 times brighter than the whole rest of the sun within minutes. And part of that relaxation also can release this big blob called a CME of energetic particles towards the Earth. So SUVI provides early warning of space weather impacts and better capabilities. I think it measures all 6 wavelengths in, I knew this just a few hours ago, but I can't remember how fast it does it. A few minutes.
It says 4 minutes.
Does it say 4 minutes? There it is, 4 minutes cadence, okay. And the resolution is about 2.5 arc seconds, which is tiny. Sure.
These early warning things, is there anything that can be done about them? Like tell people to step away from their toaster or something?
Well, that goes back to that slide I showed with the whole decision tree stuff. If there are astronauts on the way to Mars and they know a CME is coming, they can get inside a bunker. Satellite operators have put satellites in a safer configuration when space weather is going to occur, and it takes time to do those things. Power grid companies, they will not transfer huge amounts of energy from one place to another when a space weather event is going to occur. The military looks at space weather forecasts to decide, along with regular weather forecasts, as part of their decision making whether to do an operation or not, because they need to know what's going on. And if their satellite communication is disrupted, they're not going to want to do something that takes immediate response.
And there is about a day's warning, is that?
With some things, there are several days warning, three days or more, but some things are just a matter of minutes, and it's more of a response to, you can't change planning, but you can be prepared not to do something because something is occurring on the sun. And finally, there's another instrument. So this was SUVI. Over on the other side of this solar pointing platform is an instrument called EXIS that we built here at LASP. And EXIS is looking at the sun and measuring the total energy output at specific wavelengths that matter for space weather impacts on Earth. So it's looking in the X-rays and then looking in the extreme ultraviolet. These are all wavelengths that are absorbed in the upper atmosphere of the Earth and cause ionization, create the ionosphere, and they cause heating in the upper atmosphere, and they cause changes in the chemistry of the upper atmosphere. So when things like flares go off or active regions come around on the sun, the whole environment of the upper atmosphere where satellites are flying and communications is going through can change. And so we need to measure all of that. The NOAA, this is just an example. You were asking about response. Well, NOAA takes the data. So this is a measurement of the sun in 2 different wavelength bands in X-rays, and here's a flare going off. This is a pretty weak flare, but they have classes of flare levels, and they send out a blackout alert to radio operators, not just ham radio operators, but military and everybody else who uses radios to communicate, how severe the impact of that flare is going to be, and then they can adjust their response to that. And because flares happen within minutes, that has to be a real-time warning that goes out. So our instrument, like say the X-ray sensor as part of our instrument, sees a flare going off, that data comes down to Earth. We have just a few seconds of delay because of gathering the data and sending it down to Earth. It gets processed on Earth with computers in, say, half a second, and then that data product gets sent back up to GOES and through the GRB gets sent out to the rest of the country, and anybody with the right antenna to get those, it also goes out on the internet, can know in real time that a flare is occurring and how severe it is and what to do about it. So, since I'm the PI of GOES, I have to show the baby pictures. These are just different views of the instruments. You'll note that we managed to sneak in the CU-Buffalo on the instrument. This is just a clamp to hold the MLI, the blankets that make it look like a Jiffy Pop thing. We basically wrap it in insulating blankets so that we can keep it at the right temperature. But this doesn't have the blankets on. So we built 4 of them. So here's our nursery just downstairs. We had all 4 instruments. Goes R, goes S, goes T, and goes U, all sitting in our nursery downstairs, ready to go. Goes R is going to launch a month from now. Goes S maybe a year and a half from now. Goes T 5 years from now. Goes S 10 years from now. Each one of these, the challenges involved in building one of these were kind of excessive. Each one of these had to be built with 5 years of ground storage in mind. So we built this. This one has to operate just as well as that one on the day we deliver it. But we built them all at one time. It has to survive 5 years of ground storage, 5 years of on-orbit storage. So they launch this, the GOES satellites, and they have one in storage. When they turn it on after 5 years, maybe, it has to work just as well as the first day. Then we had to build it to last 20 years in space operating and work as well at the end of those 20 years as it did at the beginning. So that's a long time for a space instrument, for any instrument to work. I wish my refrigerator would last that long. We should build refrigerators at LASP. So if you want to learn more,
Lead that initiative.
yeah, you've got 30 days until GOES-R launches. You can go to this website and learn a lot. Tomorrow, 1 to 3 Eastern Time, which is that 11 to 1
11 to 1 here.
here. If you're techno-savvy, you can go on Reddit and do a live question-answer session with Greg Mant, who's the project or program director for GOES, and Steve Goodman, the GOES senior scientist. And I'm sure they'll talk all about all the great weather stuff. So I want you all to go on and ask all these questions about the great space weather stuff that's going on.
Yeah.
Finally, I had to show this. When GOES was delivered, they put it on a big airplane, wrapped in a big box, and when it came out, they took these pictures and everybody said, "It's a big Pez." So I think we win. We should get some award for being the largest Pez dispenser. And that's it. Any questions? Thank you. Yes.
You mentioned that GOES 13, 14, 15 all suffered loss of capability. Was that due to space weather? Or?
Probably not.
Probably not.
More likely just hardware design issues and hardware itself wearing out.
Just didn't last.
Yeah.
Yeah.
Or didn't. Some of the instruments didn't quite work right to begin with, but for instance, there was one of the X-ray sensors had a short in it and would work intermittently. I think it's working now though, which is really weird.
But the main weather.
But the main weather
Imager
ones,
sounders.
yeah, they're working. The space weather instruments, so NOAA has this priority call-up list, and it's the weather instruments that if one of those breaks, they bring up another satellite. But the space weather instruments, even though everybody stresses how important they are, they haven't bubbled up enough yet into the priority system to be call-up. At least not on paper. But when that one GOES satellite had a problem with its X-ray sensor, they did start making measurements with the one in storage, just to cover it.
So they brought it into.
Partially into play, yeah. And that's why you see 13 and 15 are operating and 14 is in storage. So they put back into storage the other one, yeah.
When R goes operational, will it be east or west?
I don't know. Do you know?
Whichever one is west at the time.
Yeah, I don't know if they've decided that yet. Since it's 7 months away, maybe they'll decide at the very last minute.
Where will it be during testing?
Right in the middle, in between. So they have, if you remember from that slide, I could go back all the way back. They actually have 4 positions on that slide. Come on, there we go. So goes west is at 135 west longitude, goes east is at 75. They have a checkout phase at 90 and then storage at 105. Back.
All those instruments, you've got how big a bottleneck is the bandwidth for communication?
Well, that's the joy of geostationary, is that it's just sitting straight up, and you can build a ground station and you can dump as much data as you can handle back and forth. Communications is not an issue. Let's go over to this side. I saw a few hands over here. You have a question?
Yeah, there's several pegs sticking out of the solar panel.
Several pegs.
One goes, yeah, what are those?
Maybe we can find a picture that shows them.
Not that one. It's ahead a little bit more. Nope, doesn't show it on that side. That's a drawing.
Yeah. So you thought it was on one of the pictures?
Yeah, it's
Probably in the lab. Probably
There, that
supports.
was,
Oops.
there it is.
These up here?
yeah.
I have no idea.
How would they do that?
Anybody here know? You worked at Lockheed. You worked on.
Like I said, I work on solar panels,
Yeah.
but I haven't seen pegs coming up out of it.
So that could be part of when it's all folded up, a spacer or something for the solar array, or clamps to hold it closed. Because when it launches, this is all folded up like an accordion and laying down against the spacecraft.
Yeah. Those could
And
be
then it opens
fiber-
up and
fiber
folds
latches or
out.
something like
Yeah.
that. Yeah.
Okay. More. You-
Back to Earth. Ordinary telephone systems are largely operated over cable, but part of the network is fiber now. The cable has been protected historically from lightning using clamping devices and
Right.
limiting devices. What about the fiber portion? Is the signal in a fiber optic cable subject to any of the disturbances you mentioned?
I wouldn't think so, because it's light traveling through glass or plastic.
Well,
So-
if you have ionizing radiation, if you have impurities, you might get.
But the ionizing radiation doesn't reach the ground. It's all depositing its energy high up in the atmosphere and changing the atmosphere. And so you get currents moving throughout the atmosphere, and those induce currents in the old copper wires on the ground.
Just the metallic part.
Yeah. Another one?
If you lose the east or west satellite, you have to move the other one to that position.
Yeah.
It's not functional until it gets there.
Well, I suppose they could turn it on where it is and then gradually move it. I'm not sure what their operational plan is for that. Sometimes they have all 3 operating, like over an overlap period. Because you can't, even though I said it's supposed to work perfectly when you turn it on, we'll launch it, we'll go through 6 months of commissioning. R will go into operation right away, but S is probably going to go into storage until one of the other satellites die, unless they love R so much, then they'll put it both. But when it comes out of storage, it has to go through a whole other set of commissioning type activities. Yeah.
So I understand that we at LASP executed the building of EXIS very
Yes.
well, but I'd
Of
like
course.
to know, no, we're seriously extremely well, but what were some of the uh-oh moments or big lesson learned reflections that we might have as we look back on that journey of taking on
Earned
such
value
an...
management.
Well, actually, yeah, earned value is a big one.
Had to look
This was the,
back to that.
it all was in management and QA and things like that,
Okay.
because LASP normally builds research instruments. And the customer is us, the scientists at LASP or scientists that we work with at other institutions. And so we build custom instruments for custom needs. We have quick response to those needs. We don't always do all the paperwork. With an operational instrument, you got to do all the paperwork. And you have to do lots and lots of paperwork. You have to track every part that goes into everything, every idea, every test, everything has to be documented, so that, because we're supplying a piece of equipment on a satellite that's part of our national assets, basically, and doing important operational work. So us taking on that was a new thing, and I think we did pretty well.
I think the big scientific thing was that unfortunately the instrument was designed before we had data from a much better instrument on FDL. Satellite, I think we made slightly different choices of where in the solar spectrum we looked. I know we make slightly different choices.
Oh yeah. If we were designing it, we would do it
And
differently.
If we'd
doggone
done it in-
engineers wouldn't let you make changes,
We'd done
would
it-
they?
Well, we knew that after we built the first one.
Right. So the decision to make all four at once
Had to be identical.
was something I would regret.
That's
Bec-
interesting.
But project was never going to allow us to change,
Right.
even goes U based on goes R, even though we could have started over and built a really great goes U after goes R flies and we found all the problems. But it just doesn't work that way. Everything had to be in stone with, in terms of the requirements in the design 10 years ago. Any more questions? Where's our MC? Yeah.
Can you tell me how many people here at LASP worked on this instrument?
So I can tell you how many people charged to it.
Good time on there, yeah.
When we had the most people working on it, we had 100 full-time equivalents, which probably ends up being about 200 people. And over the life of it, it probably was about 200 people. Everything from scientists to engineers and technicians. We had some students. We have calibration engineers. We have accountants. We have earned value management specialists, program managers, everything and everybody. A lawyer.
Well, I can tell you that the Waterton plant has had anywhere from 200 to 500 people working on the
On
GOES program.
the spacecraft portion of it.
Building that thing.
Yeah.
And yes, NT.
Yeah. So the whole GOES program for all four satellites, the space system, the ground system, and all the instruments, I think is at about $8 billion right now.
So
Our
LASP,
piece of it was a lot smaller than that.
so LASP really stands out in that list, of course, as being a university.
Because we're so good.
That's right. Able to execute on this national priority. What kinds of doors or opportunities do you feel this has opened up for CU or LASP and, or maybe even other academic institutions?
So we were the first university to be allowed to build an operational
Very big deal.
instrument.
UTD put stuff on DMSP.
Did they? Were they a subcontract to anybody else or a direct contract? Okay. So I
Drift meter. They had a
I did not know
proprietary
that.
instrument that nobody else had.
I did not know that. For GOES, traditionally, the contracts would only go to large corporations because they thought large corporations with these timescales involved were the only ones stable enough. The university groups were too flighty and come and go. And but I think we proved that we can do it, and we can do it not just on the technical side, but on the management side. And we hope that that leads to more such work. I could brag, but we have won awards for our performance on the GOES project, and we hope those lead to more awards of contracts. Yeah.
Are there graduate classes in project management that CU can build off of this experience to teach up and coming researchers that there's this whole management component?
So I know that the engineering school has project management courses, and the aerospace engineering department itself has a whole track of people doing management of satellite projects and satellite instrument projects. So, and some of the faculty in the aerospace department are faculty here at LASP. So the answer is yes. Everything we do does filter into the university system. Okay? Thank you.